folks, this is Mike coming back at you with another video on college algebra, some late night math time going on here. In this video, we're going to talk about inverse functions. How do we know when we have the inverse function? How can we tell what the inverse function looks like in various forms, and how can we verify it? So, before we talk about the inverse function itself and its properties and how to find it, we have to talk about when do we know we have the inverse of a given function f of x. So for a function f of x, in order for the inverse function, and note the notation that we use here for the inverse. We use f and then seemingly the exponent of -1 and then of x. To exist, the function must be 1 to 1. This is the notation for the inverse function, the inverse of a function f of x. Now there's something that people tend to confuse this with. I'm going to get into what that is later on in this video, but again, this thing right here is the inverse of f of x, sometimes read as f inverse. But anyway, the function f has to be 1 to 1 in order to have the inverse function. Now, what the heck does 1 to 1 mean? A function f of x is 1 to 1 if distinct inputs yield distinct outputs. That is to say, if you take two different x values and plug them into your function, if your function is 1 to 1, then you're going to get two completely different outputs. Mathematically, we say this two equivalent ways. If a is not equal to b, then f of a is not equal to b. F of a is not equal to f of b. Or if f of b equals f of a, then that means that b has to equal a. Now, let's just take a look at some samples here. Do the set of points below describe a one-to-one function? So again, a function is 1 to 1 if distinct inputs yield distinct outputs. So if we have two different inputs that are giving us the same output, then that is an example of a function that is not 1 to 1. We want different inputs giving different outputs. So first example here, 4 points here, 4, 1, 3, 7, 1, 0, and -2, 5. Is this a one-to-one function? Well, we see that there are no y values that repeat. We're not getting the same output from two different inputs, so yes, this is a one-to-one function here. And as we just said, the y coordinates of the points are all distinct, so this is a function that is 1 to 1. How about this guy here? 2, 1, 4, 10, 1, -2, and -2, 1. Okay, if I take a look at these 2 points here, I have the same y coordinate happening, but the x coordinates are not quite the same. I have 2 and -2. So here I have two different x values. When I plug them into this function, I get the same y value. So that's not good. And that tells us that this is not a one-to-one function. We have those two ordered pairs whose x coordinates are different, but the y coordinates are the same. So that's how we can tell if a function is 1 to 1 by looking at a set of ordered pairs. How do we know if a function is 1 to 1 just by looking at its graph? Well, a 1 to 1 function passes the horizontal line test. Now, much like we had the vertical line test to see if we had the graph of a function, and we drew vertical lines anywhere on the coordinate plane, and if they intersected the curve at only one point, each line intersected the curve at only one point, Then we knew that we had a function because it passed the vertical line test. The horizontal line test, we're going to take a look at our graph, and we are going to draw horizontal lines anywhere along that graph. And if your function, if each horizontal line, if each horizontal line intersects the graph of your function at only 1 point per line, then your function is 1-to-1. So looking at this first one here, I'm drawing some horizontal lines here. You can picture these things going every way, both ways across the x-axis. All these things going completely horizontal all the way. But look at these couple lines here that we have in the middle. We have this line intersecting here, and here, and here, as well as here, and here, and here. So these two horizontal lines, this line, or these two lines, are each intersecting the curve at 3 different points. So this is an example of a function that is not 1-to-1. That is a big fat no. We have lines that are intersecting in more than one spot. Not good. This guy here, however, as I try to make the horizontal line look actually relatively horizontal, I draw some horizontal lines here anywhere I wish. We see that each of these horizontal lines is intersecting the red curve here in only 1 point. Now, you may wonder, oh, if I get way down here, it looks like this is going to intersect in more than 1 point. It looks like they're going to overlap. Well, not actually. Yes, those lines will get very, very close. They'll get very, very close to overlapping the red curve, but it's not going to perfectly overlap it. It's only going to intersect in 1 point. So this here is an example of a 1-to-1 function. So that's how we graphically determine if a function is 1-to-1. It passes the horizontal line test. Now, let's actually talk about the inverse function. Now that we know how to figure out when we have one, now let's talk about what it is and how we find it. Let f be a function such that it takes in the input x and puts out the value y. So it picks some guy x up, it spits out some guy y. By definition, the inverse function, and again that f with the -1 in the exponent, the inverse function takes in the input y and puts out the value x. So f inverse picks up the guy that f spit out and then spits out x, which is the guy that f picked up. Symbolically, what are we saying here? We're saying f of x equals y if and only if, again, that's our double arrow, if and only if f inverse of y is equal to x. These two things are equivalent. These things are saying the exact same thing. So, again, f picks up an x, spits out a y. The inverse function takes in that y and spits out the x. Now, earlier on in the video, I said there's a common error that people tend to make when they think of the inverse function and they look at this notation here. This is not the same thing as 1 over f. This right here is the reciprocal of f. This is not the inverse of f. If I wanted to talk about this thing, we would write f of x raised to the power -1, where the entire function is in parentheses. This is the reciprocal, this is the inverse. Do not make that mistake. It is not just 1 over whatever your function is. Now, I stressed how f and f inverse work. F takes in an x, spits out a y. F inverse takes in that y and spits out the x. So basically, all the outputs of f are the inputs of f inverse, and vice versa. All the outputs of f inverse are the inputs of f. So this right here, these two things we have right here, this is a general fact about a function and its inverse. The domain of f is equal to the range of the inverse of f, and the range of f is equal to the domain of the inverse of f. So that's just a general fact that you can put in your memory banks for the future. So now, how do we actually determine what the inverse function is? First, looking at a set of ordered pairs. If a point x comma y lies on the graph of f, then the point y comma x is going to lie on the graph of f inverse. So if you're given some ordered pairs that lie on the graph of f, to find the ordered pairs that lie on the graph of f inverse, simply take the x and y coordinates of each of those points and just flip them. So I give you 5 ordered pairs here. These points lie on the graph of f. Find the corresponding points that lie on the graph of f inverse. So as we said, all we're doing is we're switching the places of the x and y coordinates. Flip those, flip those, flip those, and so on here and here. And when you do that, you get 2 comma 1, 1 comma 2, 3 comma 3, 6 comma negative 3, 9 comma 5. Again, just switch the x and y coordinates there and there as well. Very, very easy, very, very straightforward to find the ordered pairs that lie on the graph of the inverse. Here is another one. Try this guy on your own. These 5 ordered pairs lie on the graph of f. Find the points that lie on the graph of f inverse. So press pause. Once you think you have the answer, press play, and we'll see if you were right. All right, so let's see if you came up with the correct answer. You should have gotten negative 1 comma 9, 11 comma 2, 3 comma 6, negative 2 comma negative 3, and 9 comma 7. Again, very, very straightforward, very, very basic to see what is going on here. Graphically, how do we know what the inverse function looks like? So if you're given the graph of your function f and you sketch the line y is equal to x, if you take the image of f and you reflect it over that line y is equal to x, you're going to get the graph of your inverse function. You're going to get the graph of f inverse. And here I have a couple examples to show you how this works. Here, if we call our blue function f of x, that black line there is the line y equals x. So here we also have some points listed here, so we can refer back to what we just did, and we can plot the points, the corresponding points that will lie on the graph of the inverse function. 1 comma 0 goes to 0 comma 1, 3 comma 1 goes to 1 comma 3, 5 comma 2 goes to 2 comma 5, and 7 comma 3 goes to 3 comma 7. And if you just look at the blue line and the black line there, picture this thing being flipped over across that line, you get that red line right there. Picture a mirror is being held perfectly on that black line, y is equal to x, the image you'll get is that red line there. Sometimes with certain functions, it's just easier to just do a rough kind of sketch of it. Here we don't have specific points labeled, but you can see we have f here. The line y is equal to x. And then you can picture flipping that guy over across that diagonal line. So you should be able to give at least a rough sketch as to what the inverse of a function f is going to be if you're asked to. We're not looking for anything perfect. You're not being graded on your artwork here. Your drawings should just be reasonable. But the main thing that I want you to be able to know is how do we determine the inverse function algebraically? If you're just given a function f of x and you know that it has an inverse, how do you find the inverse function algebraically? Well, there's a couple steps that we take, and then there's a nice little check that we have. If you're given a function y equals f of x, first thing you're going to do is you're going to switch the places of x and y. Just wherever you had a y, you now put an x there. Wherever you had an x, you now put a y there. Then, here's where all the work happens. You now solve for y. You get y all by itself on one side. When you've done that, the resulting function you get that just has the x's, that is your inverse function. And we have a handy little check to see if our answer is indeed correct. Because for a function f and its inverse function f inverse, when you take the composition of the two, no matter which way, you should always just come up with x. So f composed with f inverse or f inverse composed with f, that should just get you x. So let's do some sample problems here to see how we come up with the inverse. So find the inverse of f of x equals x squared minus 3 and verify it. First thing we want to do is write this as y equals x squared minus 3. The f of x notation we temporarily leave out for now. For the purposes of finding the inverse, we just replace it with y. Typically, we do want to write things with f of x, but for now, we just use y. So next thing I'm going to do, I'm going to switch the places of x and y. I'm now going to put an x here, and I'm now going to put a y there. Now, second step, solve for y, get y all by itself on one side. If when you get y all by itself, the expression that contains just the x's, that is your inverse function. So I'm going to start by adding 3 onto both sides to give me y squared equals x plus 3. And now I can take the square root. And that gives me y equals the square root of x plus 3. Now some of you may be wondering, wait, don't we have plus or minus the square root of x plus 3? Technically, yes. However, when it comes to drawing graphs of functions, we only work with one of the square roots, and we only work with the positive square root. So for square roots of numbers, yes, we do have plus or minus the square root of something, but when we're using the square root as a function, we're only working with the positive square root, unless specified in other way, shape, or form. But here, as we said, we have y equals the square root of the quantity x plus 3. This is what we claim is the inverse function. This is what we claim to be f inverse of x. So now we're going to verify it. We're going to take the composition of f and its inverse both ways and verify that we come up with x. So f composed with f inverse. As a bit of a recap of taking compositions, I'm taking the inside function, or the second function listed here. I'm taking f inverse of x. I'm having that entire thing replace any x's I have in f of x. So this thing right here, that entire thing, including that square root, is going to go in for that x right there. So I have the square root of x plus 3, that quantity squared, minus 3. The square root and the square cancel each other out. So we just have x plus 3 minus 3. And then we have 3 minus 3. Those cancel out, and you just get x. So that's good one way. Let's verify the other way. Now I'm doing f inverse composed with f. I'm taking this whole thing here and substituting that in for the x inside of that square root of x plus 3. So that puts me right here. I have the minus 3 plus 3. That cancels out. And then I have the square root of x squared. Those cancel each other out. And we're just left with x. So there we go. That's our verification as to this thing right here is indeed our inverse of f given up at the top. So let's go on to another sample here. We're going to find the inverse of 2 over x minus 5, and we're going to verify it as well. Again, we're going to start off the same way. Write it as y equals 2 over x minus 5. Next, replacing the x's with y's and y's with x's. We're switching the place of x and y, and then we're going to solve for y. So here is where we switched. X equals 2 over y minus 5. Now I started to solve for y. I kicked it off by cross multiplying. X times the quantity y minus 5 gets me that there. Is equal to 2 over 1 is really what we have on the bottom there. So that's just equal to 2. I'm going to add the 5x onto both sides to give me xy equals 2 plus 5x. And then lastly, to solve for y, I just divide both sides by x. So that gets me right here, which is the same as 2 over x plus 5. This is what I claim to be f inverse. We're going to verify this and see if that is indeed correct. So taking f composed with f inverse, this was my inverse function. It replaced the x in 2 over x minus 5. Well, I have the plus 5 and the minus 5. Those subtract out to 0. So I have 2 divided by 2 over x. And dividing by a fraction is the same thing as multiplying by the reciprocal of that fraction. So this right here is also equal to 2 times x over 2. And that is equal to x right there. So that one's good. Now I have f inverse composed with f. This is 2 over x minus 5, and then plus 5. Again, the variable in the inverse was underneath the 2, so we replaced it with the entire function f. Again, dividing by a fraction is the same thing as multiplying by its reciprocal. So we get x minus 5 and then plus 5. Minus 5 plus 5 is 0, so we just get x. So this is our verification, and we do know that this guy right here is indeed our inverse. So, guys, this concludes our video on inverse functions. How do we know when we have it? How can we tell when we have it? By looking at either a graph or a set of ordered pairs. What is the definition of the or what is the definition of the inverse, and then how do we find it? Either through a set of points with a graph, or by working with the function itself and doing it algebraically. If you have any questions or comments, please be sure to reach out to me, guys. Send me emails, snail mails, texts, postcards, phone calls, rock through my window, shout really loud, drop a bomb on me, whatever you have to do. Otherwise, until the next video, take it easy, guys.